welcome to Measurement and Matter. This is our first unit in Regents Chemistry. Matter is defined as anything that has mass and takes up space. We're going to actually start our unit by just simply classifying matter, which is something you've done before in past science classes. What I think is sometimes confusing is that when you hear this definition, you think, well, isn't everything matter? Matter is most of the things we think about handling every day, but some things like energy are actually not classified as matter. They don't actually have mass, and they don't actually take up space. For now, let's focus on matter. There are two major categories of matter. There are substances, and there are mixtures. Substances can be classified as elements or compounds. Mixtures have to have more than one substance physically combined in them. We'll talk more about that in a minute. Mixtures can be classified as either homogeneous or heterogeneous. So a substance that consists of only one type of atom is what we define as being simply an element. When we say one type of atom, we mean all of the atoms in that sample have to have the same number of protons. An example would be carbon. If you have a sample of carbon, which we represent as just a C, all of the atoms in that sample of carbon have 6 protons in them. That's carbon's atomic number 6, and that's what identifies carbon. If we wanted to draw what's called a particle diagram for this, we would have simply a bunch of single atoms of carbon, all looking exactly the same. Just a caveat to this, we could also have something called a diatomic element, which we'll talk about a little bit separately, where we actually have a couple of different atoms stuck together. A compound is a substance that is made up of 2 or more types of atoms, so 2 or more different elements combined in a fixed ratio. Pardon my N. Compounds have their own unique properties. They're not the same as the elements that they come from. One of my favorite examples for this is water. Water consists of an oxygen and 2 hydrogens. Sort of has a bit of a Mickey Mouse appearance to it. What makes this a compound is H2O is always bonded in such a way where no matter how much water you have, you're always going to have a ratio of 2 H's to every 1 O. And those oxygens and hydrogens are physically combined together. Also, if we had simply hydrogen gas, or hydrogen, it would be a gas at room temperature. Oxygen's a gas at room temperature also. The minute we combine them into water, we get a substance that's all of a sudden a liquid at room temperature. So this shows us that when we combine elements chemically, we can actually make a compound with totally different properties. So our atoms bonded together have to have different number of protons to be identified as different elements. The law of constant composition says that all samples of a compound will have the same ratio of elements. So just as I mentioned before, in any sample of water, you'll always have a ratio of 2 hydrogens to 1 oxygen. A mixture is a physical combination of 2 or more substances. Those substances could be elements or compounds. So you can have a mixture of various elements. You can have a mixture of various compounds. You can have a mixture of compounds and elements. And these can be separated by physical means. A great example of a mixture is salt water. So we drew some water on the other page. If we had some other particles dissolved in here, maybe some little salt ions, we'll work on drawing these later in the year. They actually kind of attach themselves to the water a little bit. But for right now, the purpose of looking at this picture is simply we have these waters, and the waters you can see have oxygen and hydrogen actually chemically bonded together. Within this mixture, then we have other things that are just physically combined. So the blue and the greens aren't bonded to the water directly. They're just physically mixed into the same space. A little bit more on mixtures. Again, a mixture is two or more substances physically combined. The components in a mixture retain their original properties. So if you actually taste plain old salt and plain old water versus tasting salt water, you're going to notice they taste pretty much the same. The properties of those original components don't change the way they do when you combine things chemically in a compound. Components can be separated or recovered by physical means. A mixture of salt water can be separated by evaporating away the salt. Proportions of the different components may vary. So you could actually make some Kool-Aid where you put a lot of the Kool-Aid mix in. It's a very strong mixture, has a very strong flavor to it, very sweet. Or you put less of that Kool-Aid mixture in a larger amount of water. They're still both Kool-Aid. They have similar properties, same taste to them. But you'll notice that the proportions are different. One of them you would consider to be more concentrated than the other one. Homogeneous mixtures are a mixture in which your particles are uniformly distributed. An actual nice mixture of salt water is typically an example of this. If you put too much salt in, that kind of stops becoming true, but if you have just a small amount of salt and water, it will distribute itself very evenly throughout. And these types of mixtures are something we call solutions, which we'll talk more about in chemistry. This year we're going to use a whole bunch of solutions. Heterogeneous mixtures are a mixture in which the substances are not uniformly distributed. This is a very large category of mixtures. I like to think of soil as being a heterogeneous mixture. If we all went outside and took different soil samples from the courtyard, we would get all sorts of different things in those soil samples. I also like to think of chicken noodle soup. So if we had a big pot of chicken noodle soup in here, you might put a ladle in, and one scoop might have a lot of carrots, whereas another might have more of just the noodles. Just to summarize how things can be broken down. Because elements are just one simple atom, typically, or sometimes even two identical atoms stuck together, elements cannot be broken down. We do know that there are smaller particles inside of individual atoms, but under normal conditions, we can't break these down. Compounds can be broken down by chemical reactions. So you can actually do a reaction to a compound, and when doing that reaction, you'll actually separate the atoms from each other and cause them maybe to be bonded to something else. Mixtures can be separated by doing physical changes. So evaporation of water is a physical change. If you have a saltwater mixture, boiling or evaporating away that water is doing a physical change and separating the mixture by physical means. When we say we have a constant composition, since all of the atoms in an element will be the same, we're going to have a very homogeneous, very constant composition all the way through a sample of an element. We're also going to have that fixed ratio and that even distribution of things through a sample of a compound. In a mixture, our proportions and that composition can vary. So we can vary our ratios. We can make a strong mixture versus a less concentrated or weaker mixture. An element is made up of atoms with the same number of protons. A compound has at least two different elements in it that have been chemically bonded together. And a mixture is two or more substances. So we could be talking about two elements, three compounds, two elements in a compound, three compounds and an element. Doesn't matter. At least two or more substances that are physically combined. So they're not chemically bonded to each other. Some more details about some of the types of mixtures that we'll talk about this year. Solutions we spend a lot of time with. Solutions are a homogeneous mixture. We have a solvent. In this case, we typically in reagents chemistry, our solvent will be water. And we have a solute, something that gets dissolved in that water, typically a solid. In the case of salt water, if you imagine the pictures up here, if we imagine that we put some salt into water, some of these little ions kind of start to float away. They're getting dissolved into the solution. The salt is the solute, and the water is the solvent. Most of the mixtures that we deal with are what we call aqueous solutions. We abbreviate aqueous with a little AQ. It's a really important symbol to know. Aqueous solutions are homogeneous solutions with water as the solvent. Some other special types of mixtures. A colloid, we really won't talk a ton about this, but it's kind of an interesting example to think of. A colloid is a heterogeneous mixture with very small particles that don't settle out. The particles can be seen with a microscope, but actually not with the naked eye. Milk is actually a colloid. We drink milk that has been processed so that it's what we call homogenized. So it seems homogeneous when we look at it, but really, if you know a little bit more about milk, it's actually composed of water and fats and proteins that are very heterogeneous in nature. In the days of the milkman, when the milk would come, the cream would actually be on top, and you'd kind of have to mix it into the rest of the milk. It'd be like a water layer below it. So milk is actually something that appears homogeneous, but it really is actually heterogeneous. A Tyndall effect is something that we sometimes observe in some mixtures. What's interesting about the Tyndall effect is it's the scattering of light by suspended particles. So you need a decent size particle to observe the Tyndall effect. The Tyndall effect will occur in a colloid. In the second beaker in this picture, this is actually a solution right here. So what's interesting about a solution is it does not actually exhibit that scattering of light. If you had a beaker of regular water and shine light through it, you would not see that scattering. You would not see the beam. If you had a beaker of salt water, you would have the same observation. The particles are too small to scatter the light. The light passes right through and does not exhibit the Tyndall effect. Suspensions are heterogeneous mixtures with very large particles. If you've ever had coffee with grinds in it, with grounds in it, you kind of get that nasty stuff that they're showing in this picture right here. Soup, great one is salad dressing. If you think about that salad dressing that you have to shake up, and you can see these nice large particles. And they're not going to, these are going to be a little bit bigger, so they are actually going to settle out. These do appear very heterogeneous when we just look at them with the naked eye. These samples are really exhibiting the Tyndall effect as well, but sometimes the light actually can't pass through at all. You have a lot of blocking of light here by large suspended particles. Just to clear up a little bit of terminology when we look at pictures and we have to talk about identifying different types of matter. Atoms are those small single units of matter. As you may remember, they consist of protons, neutrons, and electrons. So they do have these things in them called subatomic particles, which we'll spend a lot of time talking about this year, but not so much today. These cannot be broken down under normal means unless you have something like a particle accelerator. You know, you can move electrons around a little bit in bonding, but atoms can't specifically be broken apart. Molecules are two or more atoms that are chemically linked or bonded together. And these can be broken down by a chemical change. So just to give you kind of a little bit of an idea, an atom is always just a single circle. What's kind of interesting if you look at these molecules is a lot of the molecules I've drawn up here for H2O and NH3, which again are water. The one that you might not know that you need to get familiar with is ammonia. These are compounds. And compounds always have to be molecules because you have to have multiple things bonded together. What's really interesting about oxygen gas, it's something called diatomic, and it actually exists as two atoms stuck together. It really doesn't exist as a single atom. So you can actually have a molecule of an element or a molecule of a compound. If you have just single atoms, though, you have to be talking about just a regular old element. You cannot have an atom of a compound. So the major difference between these, and this is kind of something that becomes a little bit more important this year, is that atoms are that very smallest unit of an element. They're, single atoms that we're talking about here, whereas molecules, you have to have two or more atoms that have become chemically bonded. When you're talking about elements, and we'll get a little bit more into this, elements have to be written in a specific way. So when you use your element symbols in the periodic table, either they're one capital letter. If you have a two-letter symbol, you have to be very careful that that second letter appears to be actually, a separate element, or part of the same symbol, I'm sorry. So cobalt, for example, is C lowercase o. If you're not really careful and you write those kind of the same size, now you've written carbon monoxide, and that's something very different. So you have to be careful that that second letter is smaller. If you wanted to write gallium, for example, but you write everything in capital letters, be careful to write it like this, so that that A is smaller, and we're very clear that you're talking about an element and not, a compound where you have two separate things stuck together. It's really important. All right, we're going to wrap this up by identifying some different types of matter. So please pause the video for a moment, and when you've gotten your answers, push play, and you can go ahead and check your answer. So number one, which particle diagram represents a mixture? In one, we can see that all of these groups here are the same as each other. So that's actually not two different substances. That one is representing just one compound. In number two, we have two different elements here, okay? So this is an element and this is an element, and they're physically combined with one another. So that's an example of a mixture. Picture number three is showing just one type of atom there, so that's very obviously an element. And picture number four is showing something called a diatomic element. So all of these groups, they're made of all black circles. Those are all the same as each other. That's just a regular element. We want to identify a pure substance. Pure substances can be either elements or compounds, which really means that the answer to number two is the opposite to the answer to number one. This is a compound. It's a pure substance. Element, pure substance. Element, pure substance. The way to look at this is every group inside of the picture is the same as every other group. Number three, which of the following particle diagrams represents a mixture of one compound and one element? So in this first picture, number one, we have one compound and a second compound. So this is actually a mixture of two different compounds. Picture number two, this is an element, or I'm sorry, that's a compound, that's an element. So we have a mixture of one compound and one element. Picture number three is representing a mixture of two different elements. Question number four, which particle diagram represents a diatomic or two-atom element? This is going to be choice two. Choice one is showing a compound. So it's not an element because we have two different elements bonded together, shown by those different circles. In choice three, this is actually a mixture of two different diatomic elements. So it actually becomes a mixture at that point. Choice two is actually just showing only our diatomic element.